Hello there, and welcome to the Sleepy Science Channel. Tonight's journey takes us deep into outer space, where we'll be exploring some of the most mind-blowing facts about our universe. Some of what we'll learn will be calm, like the deep oceans on distant moons. Other facts will be fierce, like black holes bigger than our entire galaxy. But each one carries a truth stranger than the last, and more beautiful than anything we could imagine. This evening, we'll wander through a collection of remarkable truths and cosmic curiosities, glimpses into worlds where rain turns to diamonds, time itself slows down, and planets drift in endless darkness. You might find yourself drifting off to sleep, or simply relaxing with this in the background. If you enjoy these videos and would like to join us for more nighttime explorations, you can like and subscribe below. And feel free to share your thoughts down in the comments. But for now, all you need to do is get comfortable. Let your breathing slow, your mind wander, and allow space itself to wash over you. Let's begin. The universe can expand faster than the speed of light. At first glance, this sounds like it breaks the laws of physics after all. Einstein's theory of relativity tells us that nothing can move through space faster than light. But the rule doesn't apply to space itself. The universe isn't just full of galaxies. The very fabric of space is stretching, and there's no speed limit for expansion. In the early moments after the Big Bang, inflation caused space to balloon faster than light could travel, carrying young galaxies away from each other at incredible speeds. Even today, the most distant galaxies are receding from us faster than light, not because they're moving through space quickly, but because space is expanding between us and them. This means there are regions of the universe we will never see. Light from those places will never reach us. The cosmos is, in a very real sense, larger than we can ever truly know. Some stars are so large they would swallow our solar system whole. Imagine a star so vast that if it replaced our Sun, its outer layers would engulf Mercury, Venus, Earth, Mars, and keep going. The largest known stars, such as Uy Scuti and Vy Canis Majoris, are red supergiants with diameters over 1,000 times greater than the Sun's. Despite their size, their outer layers are tenuous, almost like a glowing fog, and their gravity is surprisingly gentle at the surface. These giants burn fuel at a ferocious rate, living for only a few million years before exploding as supernova. Their deaths scatter heavy elements into space, seeding future solar systems with the ingredients for planets, oceans, and life. Standing on Earth, we see them only as bright pinpricks. But if you could somehow hover near one, it would fill your sky from horizon to horizon, an immense sphere of fire and gas, almost too large to comprehend. New planets can be born from the ashes of exploded stars. When a massive star reaches the end of its life, it detonates in a spectacular supernova, blasting its outer layers into space. The debris cloud is rich with heavy elements like carbon, oxygen, iron, and even gold, materials forged in the star's core over millions of years. Over time, this cosmic dust mixes with surrounding gas, eventually cooling and collapsing under gravity to form new stars and planets. In a way, planets like Earth are the direct descendants of long-dead suns. Astronomers have even spotted young planetary systems forming within supernova remnants, the newborn worlds circling stars that lit up after the explosion. This constant cycle, stars dying and planets emerging, is the reason we say we are made of star stuff. Without these ancient stellar deaths, there would be no solid ground beneath our feet, no oceans to sail, and no life to ponder its origins. Black holes can fire jets millions of light years long. Black holes are famous for swallowing everything that gets too close, but they can also be the source of some of the most powerful outflows in the universe. When matter spirals into a supermassive black hole, it heats up and produces powerful magnetic fields. These can channel part of the inflowing material into twin jets that blast out from the black hole's poles at nearly the speed of light. In extreme cases, these jets can stretch millions of light years across intergalactic space, outshining entire galaxies. They shape their environments, compressing clouds of gas to spark star formation or blasting material away to halt it. Observing these cosmic jets is like watching a black hole's heartbeat, not in light, but in raw, focused energy. They remind us that even in the darkness of a black hole, forces exist that can reach unimaginably far into the cosmos. Scientists believe it can rain solid diamonds on other worlds. On planets like Neptune and Uranus, conditions deep in the atmosphere may be so extreme that carbon atoms are squeezed into diamond crystals. As these diamonds form, they could fall like hail, sinking slowly through layers of gas until they eventually dissolve in the planet's hot, pressurized interior. Laboratory experiments on Earth have recreated these conditions using powerful lasers to compress methane into shimmering diamond dust. The idea isn't pure speculation. The physics checks out, and similar processes might happen on other carbon-rich worlds throughout the galaxy. Some scientists think entire diamond bergs could drift in the hidden layers of these planets. While we'll never harvest them, knowing they exist turns distant planets into glittering, alien landscapes in our minds, places where storms are measured not in raindrops or snowflakes, but in gemstones, tumbling silently through a deep blue sky. The Milky Way and Andromeda are doomed to collide. Right now, the Andromeda Galaxy is over 2 million light-years away, but it's moving toward us at about 400 kilometers per second. In roughly 4 billion years, it will collide with the Milky Way. This won't be the kind of collision we imagine on Earth. Stars are so far apart that very few will physically hit each other. Instead, the galaxies will merge, their shapes twisting into tidal tails and great arcs of stars, before settling into a new, larger galaxy, sometimes called Milkomeda. The night sky during this cosmic dance would be breathtaking, filled with sprawling ribbons of light. Our Sun, if it still exists then, may find itself in a completely new orbit. These events are common in the universe, and in fact, the Milky Way itself is the product of many such mergers over its long history. Neutron stars spin so fast they warp space around them. When a massive star collapses, it can leave behind a neutron star, a sphere only about 20 kilometers across, yet more massive than the Sun. Some neutron stars, called pulsars, rotate hundreds of times per second. This rapid spin, combined with their immense gravity, distorts the very fabric of space-time around them. Pulsars emit beams of radiation from their magnetic poles, and as they spin, these beams sweep across space like the beams of a lighthouse. If Earth lies in the path of one of these beams, we detect a regular pulse, sometimes more precise than an atomic clock. These cosmic beacons help astronomers map the galaxy and even test theories of gravity. Standing near one, if you could somehow survive the crushing gravity, would be like standing beside a mountain spinning at nearly the speed of light. Entire galaxies can hide in almost complete darkness. Not all galaxies blaze with starlight. Some, known as dark galaxies, contain huge amounts of gas but few stars. Without bright stellar populations, they're nearly invisible, revealed only when their gas is detected by radio telescopes or when their gravity bends the light of more distant objects. These dark galaxies are thought to be relics from the early universe, frozen in time before they could form many stars. Studying them could reveal why some galaxies flourish while others fade into obscurity. They may also hold clues to how dark matter shapes cosmic structures. To the naked eye, they would be invisible, hidden in the blackness of space. Vast, silent cities of gas and dust that never truly lit their lamps. Their existence is a reminder that in the universe, not everything worth knowing can be seen. Rogue planets drift through space without a star. Most planets orbit stars, but rogue planets wander the galaxy alone, pulled free from their systems by gravitational encounters. Without a sun, they drift through eternal night, their only warmth coming from residual heat left over from their formation, or, in some cases, from radioactive decay deep inside. Some may still have thick atmospheres or subsurface oceans insulated by ice. Estimates suggest there could be more rogue planets than stars in the Milky Way, entire hidden worlds roaming unseen. These lonely wanderers are nearly impossible to detect directly, but astronomers catch glimpses of them when they pass in front of distant stars, briefly dimming their light. The idea of a planet floating through interstellar space with no sunrise or sunset is haunting. Yet such worlds might still be capable of hosting life, sealed away in warm pockets beneath their frozen surfaces, drifting endlessly through the dark. The sun's atmosphere is hotter than its surface. It seems impossible. The sun's visible surface, the photosphere, burns at about 5,500 degrees Celsius, yet its outer atmosphere, the corona, reaches over 1,000,000 degrees. Scientists are still working to fully explain this paradox. One leading theory is that powerful magnetic fields on the sun twist and snap, releasing bursts of energy that heat the corona. This layer of hot plasma extends millions of kilometers into space, shaping the solar wind that streams through the solar system. The corona becomes most visible during a total solar eclipse, when the moon blocks the sun's bright surface and reveals a ghostly halo of white light. This superheated atmosphere plays a crucial role in space weather, which can disrupt satellites and power grids on Earth. Understanding how the corona stays so hot may also help us unlock new secrets about the sun's inner workings. Some stars flicker like cosmic lighthouses. Variable stars change their brightness over time, sometimes in predictable patterns, sometimes chaotically. In some, the flickering is caused by pulsations in the star's outer layers, expanding and contracting in rhythmic cycles. In others, spots or flares on the surface can cause changes in light, much like sunspots on our sun. Certain types, such as Cepheid variables, are so reliable that astronomers use them to measure the distances to faraway galaxies. Then there are eclipsing binaries, pairs of stars orbiting each other, where one regularly passes in front of the other, dimming its light. For early astronomers, these flickers were mysterious, even alarming. Today, we know they are simply another face of stellar life, revealing how stars burn, evolve, and sometimes dance with companions. Watching a variable star's light rise and fall is like listening to the heartbeat of the cosmos, slow and steady across the ages. There are storms on Jupiter, bigger than Earth. The most famous is the Great Red Spot, a swirling, crimson-hued storm that has raged for at least 3 centuries. This massive anticyclone is so large that 3 Earths could fit inside it. Winds inside the storm reach hundreds of kilometers per hour, and its reddish color is thought to come from complex chemical reactions in Jupiter's upper atmosphere. Jupiter's storms are powered by the planet's rapid rotation and internal heat, creating turbulent bands of clouds that wrap around the gas giant. Unlike storms on Earth, which eventually lose energy, Jupiter's storms can persist for decades or even centuries because there's no solid surface to slow them down. In recent years, the Great Red Spot has been shrinking, but other storms, some nearly as large, continue to churn across the planet's face, reminding us that Jupiter is a world of immense and constant atmospheric drama. A single spoonful of neutron star material would weigh billions of tons. Neutron stars are the remnants of massive stars that collapsed under their own gravity, squeezing their mass into an object only about 20 kilometers wide. In these extreme conditions, protons and electrons merge into neutrons, creating matter so dense that a single teaspoonful would weigh billions of tons on Earth. The gravity at the surface is crushing, strong enough to bend light and distort time. Neutron stars can spin incredibly fast, and some emit beams of radiation that sweep across the sky like lighthouses. If you could somehow bring a fragment of neutron star to Earth, it would immediately collapse into a catastrophic explosion. Our planet's crust couldn't possibly contain such density. These stellar remnants are among the strangest and most extreme objects in the universe, pushing the boundaries of what we think is physically possible. Saturn's rings are slowly disappearing. The shimmering rings of Saturn may be only temporary. Made mostly of water ice mixed with dust and rocky debris, the rings are constantly bombarded by micrometeoroids and pulled inward by Saturn's gravity. Material from the rings falls toward the planet as a ring rain, disappearing into its upper atmosphere. This process, combined with gradual spreading of the ring particles, means the rings could vanish in as little as 100 million years, a blink in cosmic time. Observations from the Cassini spacecraft revealed that the rings are much younger than Saturn itself, possibly forming from a shattered moon or comet. For now, they remain one of the most beautiful sights in the solar system, reflecting sunlight in pale, icy arcs that can be seen even through small telescopes. But they are a reminder that in space, even the most magnificent structures do not last forever. Massive stars can collapse in seconds. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses at incredible speed, reaching a fraction of its original size in less than a second. This sudden collapse generates a shockwave that blasts the star's outer layers into space, creating a supernova. The energy released in this moment can briefly outshine an entire galaxy. Depending on the star's mass, the cool remnant becomes either a neutron star or a black hole. This process is not slow or gentle. It is one of the most violent events in the universe, transforming a stable star into a rapidly expanding cloud of gas and dust in moments. These explosions scatter heavy elements through space, seeding future generations of stars and planets. Without these brief but powerful deaths, the universe as we know it would not exist. Space itself has a subtle background glow from the Big Bang. Everywhere we look in the universe, even in the darkest, emptiest regions, there is a faint glow of microwave radiation. This is the cosmic microwave background, the afterglow of the Big Bang, stretched into long wavelengths by the universe's expansion. Discovered by accident in 1965, it's a snapshot of the cosmos when it was just 380,000 years old. At that time, the universe cooled enough for atoms to form, allowing light to travel freely for the first time. Tiny variations in this glow reveal the seeds of galaxies and clusters we see today. Astronomers map this faint radiation with incredible precision, using it to understand the universe's age, composition, and shape. It's a quiet reminder that all of space is filled with the memory of its own birth, still whispering across more than 13 billion years. The moon is drifting away from Earth. Each year, the moon moves about 4 centimeters farther from Earth. This slow drift is caused by tidal interactions. As the moon's gravity pulls on our oceans, it creates tidal bulges that slightly speed up the moon's orbit while slowing Earth's rotation. In the distant past, the moon was much closer, and days on Earth were significantly shorter. Fossil evidence from ancient coral growth patterns supports this, showing that hundreds of millions of years ago, a year contained more days because each one was shorter. Over billions of years, the increasing distance will change the appearance of total solar eclipses, eventually making them impossible. Though the change is imperceptible in a human lifetime, the Moon's gradual journey outward is a reminder that even the relationship between Earth and its closest companion is not fixed forever. Some black holes spin nearly at the speed of light. Black holes can rotate, and the fastest ones spin at rates approaching the speed of light. This rotation drags space-time itself around with it, an effect known as frame dragging. In such environments, nothing can remain still. Everything is forced to move in the direction of the spin. The spin of a black hole is determined by the angular momentum of the star that formed it, and by material it has consumed since. High spin rates can create more powerful jets and affect how matter falls into the black hole. Measuring this spin is challenging, but astronomers use the light from the material in the black hole's accretion disk to infer it. Some black holes spin so fast that their event horizons, the points of no return, are significantly smaller than they would be if the black holes were not rotating at all. The largest known star could hold millions of Earths inside it. Scuti, one of the largest known stars, is a red supergiant so vast that if placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. With a diameter more than 1,700 times greater than the Sun's, it has enough volume to fit millions of Earths inside. Despite its size, its outer atmosphere is incredibly diffuse, a glowing veil of gas drifting away into space. Stars like Scuti burn through their fuel quickly, living only a few million years before collapsing in a spectacular supernova. These stellar giants are rare and fleeting, but they give us a sense of just how extreme the universe can be. Observing one is like watching a living mountain of fire, so large it could engulf the worlds we know without even noticing. We can hear the echo of the universe's birth. The universe carries a faint, ancient signal, the cosmic microwave background, a whisper from when the cosmos was just 380,000 years old. Though it is light, not sound, scientists can translate its fluctuations into audible tones, turning the data into something we can hear. These sounds represent tiny ripples in the density of the early universe, which later grew into galaxies, stars, and planets. Listening to this echo is like hearing the aftershock of creation itself, stretched and softened by more than 13 billion years of cosmic expansion. The pattern is uniform across the sky, yet filled with minute variations that hold the keys to the universe's composition, age, and fate. Every photon in this background has traveled since the dawn of time, carrying with it the memory of the moment the first light broke free. Mars has the tallest volcano in the solar system. Olympus Mons rises nearly 22 kilometers above the Martian surface, about 2.5 times the height of Mount Everest. This colossal shield volcano spans roughly 600 kilometers across, making it as wide as the entire state of Arizona. Its slopes are gentle, allowing for the slow, steady buildup of lava flows over millions of years. Mars's lower gravity, lack of tectonic plate movement, and long-lasting volcanic activity allowed Olympus Mons to grow far larger than any volcano on Earth. Though it is considered dormant, its relatively young geological features suggest it could erupt again in the distant future. Standing at its base, the summit would be invisible beyond the curve of the planet. It is a monument to the power of planetary geology, frozen in time beneath the thin, rust-colored skies of Mars. Some comets come from beyond the solar system. Most comets originate from the Oort cloud or the Kuiper belt, but in recent years, astronomers have discovered visitors from interstellar space. Objects like Oumuamua and Comet Borisov arrived on hyperbolic trajectories, too fast to be bound by the sun's gravity. These icy wanderers likely formed around distant stars before being ejected into the void by gravitational interactions. Their journeys across interstellar space may have taken millions of years before they passed briefly through our neighborhood. Studying them gives us a rare glimpse into the chemistry and history of other planetary systems. Unlike most comets, whose returns we can predict, these interstellar travelers are one-time visitors, drifting into our skies for weeks or months before fading forever into the dark between the stars. The dark side of the moon isn't always dark. The phrase "dark side of the moon" is misleading. Every part of the moon receives sunlight at some point during its month-long orbit. The far side, which always faces away from Earth due to tidal locking, experiences the same cycle of day and night as the side we see. However, because we can never see it from Earth, it remained a mystery until the Soviet Luna 3 spacecraft photographed it in 1959. The far side looks very different, with fewer Maria, the dark, volcanic plains, and far more craters. It is dark only in the sense of being hidden from our constant view, a reminder of how language can shape our perception of space. The reality is that both sides of the moon share the same cold mornings, bright noons, and long, shadowed nights. The Milky Way smells of rum and tastes of raspberries. In a giant cloud of gas and dust near the center of our galaxy, astronomers have detected ethyl formate, a chemical that smells like rum and tastes like raspberries. This compound is found in Sagittarius B2, a massive molecular cloud where new stars are forming. While you wouldn't want to breathe or taste anything there, it's a toxic mix in reality. The discovery shows that some of the building blocks of familiar flavors and scents exist naturally in space. Such molecules form on the surfaces of dust grains and are released into space when the grains are warmed. It's a whimsical reminder that the same chemistry that flavors our food can also be found light years away, drifting between the stars. Spacecraft have left the solar system and entered interstellar space. NASA Voyager 1 and Voyager 2 probes, launched in 1977, have both crossed the boundary. Known as the heliopause, the point where the solar wind from our sun gives way to the interstellar medium. Voyager 1 reached this milestone in 2012, followed by Voyager 2 in 2018. These spacecraft are now traveling through a region where the influence of other stars begins to mingle with our own. Their instruments still send back data, offering humanity its first direct measurements of the space between the stars. Each carries a golden record containing sounds, images, and greetings from Earth. A message in a bottle for any distant civilization that might find them. Though they have enough power to operate for only a few more years, their silent journeys will continue for billions of years. Some asteroids are packed with precious metals, while most asteroids are made of rock or carbon-rich material. A rare class called N-type asteroids are composed largely of metals such as iron, nickel, and even platinum. One famous example, 16 Psyche, is thought to be the exposed core of a failed protoplanet stripped of its outer layers. Its estimated metal content is so great that, in theory, it could be worth more than all the money on Earth. Though, of course, mining and transporting it would be an extraordinary challenge. Studying these metallic asteroids can reveal how planetary cores form and how the early solar system evolved. They may also be future targets for space mining missions, offering resources for building in space rather than hauling materials from Earth. A day on Venus lasts longer than its year. Venus rotates so slowly on its axis that one full rotation takes about 243 Earth days. However, it orbits the Sun in just 225 Earth days, meaning a day on Venus is longer than its year. Even stranger, Venus rotates in the opposite direction to most planets, so the Sun appears to rise in the west and set in the east. This slow spin may be the result of ancient collisions or tidal interactions with the Sun. combined with its thick, carbon dioxide-rich atmosphere and extreme quiet. Surface temperatures. Venus's rotation creates one of the most inhospitable environments in the solar system. Yet beneath its clouds, volcanic landscapes and towering mountains hint at a complex geological history we are only beginning to understand. The coldest place in the universe is colder than empty space. In the Boomerang Nebula, located about 5,000 light-years away, temperatures plunge to just 1 degree above absolute zero, colder than the faint heat left over from the Big Bang. This deep freeze occurs because gas from a dying star is expanding so rapidly that it cools beyond the background temperature of space itself. The Boomerang Nebula's eerie, hourglass-shaped cloud glows faintly in visible light, but shines brightly in radio wavelengths. It is a natural cosmic freezer, preserving its gas and dust in conditions almost unimaginable on Earth. Eventually, the star at its center will heat up again, dispersing the nebula, but for now it remains the chilliest known place in the universe. Entire stars can be eaten by black holes when a star drifts too close to a doubler. Supermassive black hole. Tidal forces can tear it apart in a process called a tidal disruption event. The star's material is stretched into a long, glowing stream, with much of it spiraling into the black hole's accretion disk. As the gas falls inward, it heats to millions of degrees, emitting powerful bursts of light that can outshine the galaxy for months. The rest of the star's remains may be flung back into space at incredible speeds. These cosmic meals are rare for any given galaxy, but when they happen, they offer astronomers a chance to study black holes in action. The event is both beautiful and violent, a reminder that even massive, luminous stars are fragile when faced with the gravitational hunger of a black hole. Saturn could float in a large enough ocean. Saturn's average density is less than that of water, about 0.69 grams per params, cubic centimeter, making it the only planet in the solar system that would float if there were an ocean large enough to hold it. This low density comes from its composition, mostly hydrogen and helium, with only a small core of heavier elements. Of course, no real ocean could contain a planet, but the thought experiment shows how different Saturn is from rocky worlds like Earth. Its gaseous nature also means it has no solid surface. If you descended into its atmosphere, you would pass through layers of cloud and increasing pressure until you were crushed by its deep interior. The planet's lightness contrasts with the immense beauty of its rings, making Saturn one of the most striking worlds in the night sky. The hottest planet in the solar system isn't the closest to the Sun. Mercury may be nearest to the Sun, but Venus holds the record for the highest average surface temperature, about 465 degrees Celsius. This is due to its thick atmosphere of carbon dioxide, which traps heat through a runaway greenhouse effect. Clouds of sulfuric acid reflect sunlight, but they also lock in the heat already on the surface, preventing it from escaping into space. The result is a world where metal melts, and any spacecraft lasts only hours before succumbing to the heat. Venus's extreme conditions make it a cautionary example of how greenhouse gases can transform a planet. Yet beneath its hostile skies lies a landscape of vast plains, volcanoes, and mountains, hinting at a geologic complexity that continues to intrigue scientists. Some moons are geologically active. Not all moons are frozen, dead worlds. Jupiter's moon Io is the most volcanically active body in the solar system, with hundreds of active volcanoes powered by tidal heating from Jupiter's immense gravity. Saturn's moon Enceladus has geysers that spray water vapor and ice particles into space, feeding Saturn's ring. Even Neptune's moon Triton shows signs of past cryovolcanism, where water, ammonia, or methane erupt instead of molten rock. Geological activity suggests that some moons may have internal heat sources capable of supporting subsurface oceans, and potentially life. These active moons are windows into processes that occur far from the warmth of the sun, proving that the solar system is far more dynamic than it might appear at first glance. You could fit all the planets between Earth and the Moon. The average distance between Earth and the Moon is about 384,000 kilometers. Surprisingly, this is enough space to line up all the other planets in the solar system, Mercury through Neptune, side by side, with a little room to spare. This mental image challenges our sense of scale, reminding us that even our close celestial neighbor is much farther away than it appears. The Moon's apparent size in the sky is an illusion created by perspective in reality. Space is vast, even in our own cosmic backyard. Thinking about this scale can make lunar missions feel all the more impressive. Every spacecraft to the Moon has crossed a gap large enough to hold the worlds of our solar system in a single row. The Milky Way is surrounded by a halo of invisible matter. Our galaxy doesn't end where the stars fade from view. Surrounding it is a massive halo of dark matter, an invisible form of mass that doesn't emit or absorb light, but exerts a powerful gravitational pull. This halo extends far beyond the visible disk of the Milky Way, shaping the orbits of stars and influencing how galaxies form. We can't see dark matter directly, but its presence is revealed through its effects on the motion of stars and gas. Some estimates suggest the halo contains much more mass than all the stars in the galaxy combined. Without it, the Milky Way would fly apart under its own rotation. This unseen structure is a reminder that most of the matter in the universe is something we cannot see, at least not yet. Time moves differently in strong gravity. According to Einstein's general theory of relativity, time passes more slowly in stronger gravitational fields. This means that near a massive object, such as a black hole or even Earth's surface, time moves slightly slower compared to regions with weaker gravity. The effect is tiny on Earth but becomes dramatic near extreme masses. In theory, an astronaut orbiting close to a black hole could experience only a few hours, while years pass for someone far away. This phenomenon, known as gravitational time dilation, has been confirmed by experiments with atomic clocks on airplanes and satellites. It's not just a science fiction idea, it's a measurable reality that links space, time, and gravity in a single, elegant framework. The universe is full of wandering black holes. While supermassive black holes anchor the centers of galaxies, smaller black holes can roam freely through space. Some form from the collapse of massive stars and drift through the galaxy, invisible unless they interact with surrounding matter. Others may be ejected from their home systems by gravitational encounters or even the recoil from black hole mergers. Detecting them is difficult, but astronomers have begun identifying candidates by watching for their gravitational lensing effects on background stars. These wandering black holes are like cosmic ghosts, drifting silently through the galaxy, each one a point where space and time fold in on themselves. Some stars are powered by helium instead of hydrogen. Most stars fuse hydrogen into helium in their cores, but when the hydrogen runs out, heavier stars can ignite helium fusion, creating carbon and oxygen. In rare cases, stars lose their outer hydrogen layers entirely, revealing helium-burning cores from the start. These helium stars shine hotter and bluer than normal stars and have much shorter lifespans. They are thought to form through mass transfer in binary systems, where one star strips the outer layers from its companion. Studying them gives astronomers a window into late-stage stellar evolution and the processes that lead to supernova explosions. Astronomers have detected ternets around pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radiation. And in 1992, astronomers found planets orbiting one. the first confirmed exoplanets ever discovered. These pulsar planets are exposed to intense radiation and would be inhospitable to life as we know it, but their existence shows that planets can form in even the most extreme environments. They may be remnants of a destroyed star or material captured after the pulsar's birth. The precision of pulsar timing makes it possible to detect the tiny gravitational tug of orbiting planets, revealing their presence even light years away. Light from distant stars can bend around massive objects. In Einstein's general relativity, mass bends the fabric of spacetime, and light follows that curve. This means a massive object, such as a galaxy or black hole, can act like a lens, bending and magnifying the light of something behind it. Known as gravitational lensing, this effect allows astronomers to see galaxies so distant that their light would otherwise be too faint to detect. In some cases, the background object appears stretched into arcs or multiplied into several images. Gravitational lensing not only gives us a cosmic magnifying glass, but it also lets scientists map the distribution of dark matter, which causes additional bending despite being invisible. It's a reminder that space is not a flat stage, but a dynamic, warped landscape, where light itself is guided by the invisible curves of gravity. Our Sun is just one of hundreds of billions of stars in the Milky Way. From Earth, the Sun feels unique, but it is only one star among an estimated 200 to 400 billion in our galaxy. Many are larger or smaller, hotter or cooler, younger or older. Some have planets, some do not. The Sun is a G-type main sequence star, fairly ordinary by cosmic standards, but perfect for sustaining life on Earth. The sheer number of stars in the Milky Way means that even if a tiny fraction have habitable planets, there could be millions of worlds where life might arise. Every point of light we see in the night sky belongs to this vast stellar city, and most of the galaxy remains hidden from our view, its stars too faint or too far away for the naked eye to detect. There are stars that appear to blink out of existence. Astronomers have observed stars in old photographic plates that no longer seem to exist today. Some may have undergone dramatic changes, such as fading into white dwarfs or collapsing into black holes. Others might be explained by observational errors or unusual transient events like supernova that were missed in real time. But a few cases remain mysterious, with no obvious explanation. These vanishing stars spark speculation about exotic phenomena, from failed supernova to entirely new kinds of astrophysical events. They remind us that even with our modern technology, the universe can still surprise us, and that our cosmic census is far from complete. Entire galaxies can merge into one. When galaxies collide, their stars rarely collide directly because of the vast distances between them. Instead, their mutual gravity pulls them into new shapes, creating streams of stars and clouds of gas that ignite bursts of star formation. Over time, sometimes hundreds of millions of years, the galaxies settle into a single, larger system. The Milky Way itself is the product of many past mergers and will one day merge with Andromeda. These cosmic unions reshape the architecture of the universe, recycling old stars, creating new ones, and building ever larger structures in the cosmic web. Space can stretch and shrink without anything moving. In the framework of general relativity, space is not a fixed backdrop. It can expand, contract, and warp. During cosmic inflation, just after the Big Bang, space expanded faster than light, carrying matter with it. Even today, the expansion of the universe is stretching the distances between galaxies. On smaller scales, the opposite can happen. Gravity can pull matter together, shrinking space locally and binding galaxies into clusters. This means objects can move apart without actually traveling through space. Instead, the space between them is growing. It's one of the most counterintuitive aspects of modern cosmology, showing that our everyday notions of movement don't always apply on a cosmic scale. The Andromeda Galaxy is already visible to the naked eye. On a dark, clear night, far from city lights, you can see a faint, elongated smudge in the constellation Andromeda. This is the Andromeda Galaxy, over 2 million light-years away, the most distant object visible without a telescope. What you're seeing is the combined light of 1 trillion stars, shining across unimaginable distances. In photographs, Andromeda reveals spiral arms, dust lanes, and satellite galaxies, but even to the naked eye, its presence is humbling. It's not just a point of light like the stars in our own galaxy. It's an entire island universe, slowly making its way toward us for an eventual merger billions of years from now. Jupiter's magnetic field is strong enough to shrink your phone battery. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times more powerful than Earth's. It creates intense radiation belts filled with high-energy particles, dangerous to both spacecraft and humans. If you could somehow stand within this field with an electronic device, the charged particles would quickly interfere with its operation, potentially draining or damaging it. This magnetic shield is generated by Jupiter's rapidly rotating metallic hydrogen interior and extends millions of kilometers into space, even capturing some of Jupiter's moons within its influence. It's a planetary-scale force field, invisible but immensely powerful. Some stars explode without warning. While many supernovae are predictable in theory, occurring when a star reaches a certain stage in its life, some appear to happen unexpectedly. These may be caused by sudden instabilities in the star's core, or by interactions with a close companion star that trigger collapse. In rare cases, the star might even explode more than once, ejecting outer layers in stages. Such events challenge our understanding of stellar evolution and remind us that even well-studied stars can harbor surprises. Observing them helps refine our models of how stars live and die. There are planets made almost entirely of gas. Gas giants like Jupiter and Saturn are composed mostly of hydrogen and helium, with only small rocky cores deep inside. Beyond our solar system, astronomers have found even more extreme examples. Planets larger than Jupiter, with densities so low they could almost float in water. These superpuff planets may have thick atmospheres and tiny solid cores, making them resemble miniature stars more than Earth-like worlds. They often orbit close to their stars, where intense heat can inflate their atmospheres even further. Studying them helps us understand how planetary systems form and evolve. The universe may be infinite in size. Current observations suggest that on large scales, the universe is flat, meaning it could extend forever. If true, there may be regions so far away that their light will never reach us, no matter how long we wait. An infinite universe would contain endless variations of galaxies, stars, and planets, and perhaps even regions where conditions are identical to our own. While we cannot directly confirm infinity, the possibility stretches our imagination to its limits. It's a concept both exhilarating and humbling. No matter how far we look, there might always be more. We can see galaxies as they were billions of years ago. Light doesn't travel instantly. It moves at about 300,000 kilometers per second. Across the vast distances of space, this means we see celestial objects not as they are now, but as they were when their light began its journey. When we look at a galaxy 10 billion light-years away, we're seeing it 10 billion years in the past. The Hubble Space Telescope has captured images of tiny, faint galaxies from a time when the universe was less than 1 billion years old. These ancient snapshots show young galaxies bursting with new stars, colliding and evolving into the giants we see nearby today. In a sense, telescopes are time machines, allowing us to look back into an era long before Earth even existed. The farther we look, the closer we get to glimpsing the universe's earliest moments, frozen in light that has crossed cosmic history. Space is not completely empty. The vastness between stars and galaxies might seem like a perfect vacuum, but space is never truly empty. Even in the loneliest stretches of intergalactic space, there are stray atoms, particles, and the faint glow of background radiation from the Big Bang. In our solar system, the space between planets is filled with the solar wind, a constant stream of charged particles from the sun. Cosmic rays from distant supernova and other energetic events also pass through, striking spacecraft and even our own planet. On larger scales, immense filaments of gas and dark matter connect galaxies like threads in a cosmic web. These sparse but ever-present contents of space are invisible to the naked eye, yet they shape the movement, chemistry, and temperature of the universe. Even in what seems like nothingness, the universe hums with a faint and constant presence. The largest black holes are billions of times more massive than the Sun. At the centers of many galaxies lie supermassive black holes, with masses ranging from millions to billions of suns. The largest known, TON 618, is estimated at over 60 billion solar masses, a gravitational anchor so powerful it shapes the movement of entire galaxies. These titans likely grew over billions of years, devouring stars, gas, and smaller black holes, or forming in the dense hearts of early galaxies. While their event horizons are immense, larger than our entire solar system, they remain invisible, their presence revealed only by the behavior of nearby matter. Gas spiraling into these giants heats to extreme temperatures, emitting radiation that can be detected across the cosmos. Despite their name, supermassive black holes are not empty voids, but regions where gravity overwhelms all other forces, creating a point from which not even light can escape. There are galaxies that spin in the opposite direction to most others. Most spiral galaxies, including our Milky Way, rotate in a direction determined by how they formed. But astronomers have discovered rare galaxies whose stars and gas rotate the wrong way compared to the majority. These counter-rotating galaxies may have experienced dramatic collisions or mergers that flipped their rotation, or they may have absorbed streams of gas moving in an opposing direction. In some cases, only certain parts of the galaxy, like the inner disk or outer halo, spin backwards, creating a cosmic dance of competing motions. These unusual rotations provide clues about the violent and unpredictable events in galactic history. Studying them helps astronomers piece together how galaxies grow and evolve, showing that the universe's structures are shaped as much by chaos and chance as by orderly formation. Cosmic rays pass through your body every second. Invisible and harmless in small doses, cosmic rays are high-energy particles, mostly protons, that constantly rain down from space. They originate from powerful events like supernova, colliding neutron stars, and even active galaxies with supermassive black holes. When they strike Earth's atmosphere, they create showers of secondary particles that reach the ground and even pass through our bodies. Right now, several cosmic ray particles are traveling through you, unnoticed. Astronauts beyond Earth's protective atmosphere experience them more intensely, sometimes seeing flashes of light in their vision as particles interact with their eyes. While our planet's magnetic field and atmosphere shield us from most harmful effects, cosmic rays are a reminder that we live in a universe filled with unseen forces constantly passing through us, connecting us in a small way to the most energetic events in the cosmos. Some stars are so dense they defy imagination. Neutron stars are the remnants of massive stars compressed into an object just 20 kilometers across, yet containing more mass than the Sun. In these conditions, atoms are crushed, and matter exists as a sea of neutrons packed so tightly that a single teaspoon would weigh billions of tons. The density is so extreme that its gravitational pull distorts the path of light and slows time. The surface is a thin crust over a core that may contain exotic states of matter we have never recreated on Earth. Neutron stars can spin hundreds of times per second, generating intense magnetic fields that shape their surroundings. They are the edge of physics as we know it, places where our current understanding of matter and energy begins to break down. A single supernova can outshine an entire galaxy. When a massive star dies in a supernova, the explosion can release more energy in a few weeks than the sun will emit in its entire lifetime. For a brief period, the dying star can outshine all the billions of stars in its host galaxy combined. These cosmic explosions are visible across vast distances and serve as important markers for measuring the expansion of the universe. The shockwaves from supernova sweep through space, triggering the birth of new stars in nearby gas clouds. They also forge heavy elements, iron in your blood, gold in jewelry, and scatter them across the cosmos. Without supernova, planets like Earth would lack the raw materials for life. They are both an end and a beginning, cosmic punctuation marks in the story of stellar evolution. The northern lights are caused by solar winds. Auroras occur when charged particles from the sun, carried by the solar wind, interact with Earth's magnetic field and atmosphere. These particles are guided toward the polar regions, where they collide with atoms of oxygen and nitrogen high in the atmosphere. The energy from these collisions is released as light, painting the sky in shimmering curtains of green, pink, purple, and red. The exact colors depend on the type of atom and the altitude of the interaction. Auroras are not unique to Earth. They have been observed on Jupiter, Saturn, and even distant Uranus. They are living proof that the Sun and Earth are connected in a constant exchange of energy, and they remain one of nature's most beautiful and hypnotic displays. There are moons with atmospheres thicker than Earth's. Saturn's moon Titan has an atmosphere denser than our own, composed mostly of nitrogen with traces of methane and other gases. Its thick haze shrouds the surface, hiding a landscape of lakes, rivers, and seas of liquid methane and ethane. The pressure on Titan's surface is about 1.5 times that of Earth's, and temperatures are far below freezing. Despite the cold, Titan's atmosphere supports a methane cycle similar to Earth's water cycle, with clouds, rain, and seasonal changes. This dense atmosphere and complex weather make Titan one of the most Earth-like worlds in the solar system, albeit one that is deeply alien. The edge of the observable universe is moving away from us. Because the universe is expanding, the most distant regions are receding from us faster than the speed of light, not because they're moving through space quickly, but because space itself is stretching. This means the edge of what we can observe is constantly changing. Light from beyond a certain distance will never reach us, no matter how long we wait. Currently, the observable universe has a radius of about 46 billion light-years, but its true size may be much greater, possibly infinite. As time passes, more galaxies will slip beyond our reach, leaving only those nearby visible. It's a reminder that the night sky we see today is just a temporary view, and that the cosmos will look very different to observers in the far future. Dark energy is pushing the universe apart. In the late 1990s, astronomers discovered something astonishing. The expansion of the universe isn't slowing down under gravity. As expected, it's speeding up. The cause appears to be a mysterious phenomenon called dark energy, which makes up about 70% of the cosmos. Unlike dark matter, which pulls with gravity, dark energy acts as a kind of cosmic repulsion, stretching space itself. Its exact nature is unknown, but its effects are everywhere. Distant galaxies are receding faster than they once did, and over billions of years, dark energy will push them so far away that their light can never reach us. In the far future, the universe could become a lonely